will invite Viktor Brus from Kazakhstan, who has an invited talk on a simple approach for unraveling optoelectronic processing in organic solar cells. We have plenty of time, Viktor, so take your time. And welcome, Viktor.
Thank you very much for nice introduction. First, I would like to thank for inviting me and letting such an opportunity to share with you my recent research in the field of organic optoelectronics. Let me try to share my screen. Oh, it's written here that someone should stop sharing his screen. I believe maybe Professor Demchenko didn't stop sharing his screen.
Professor Demchenko, if you still have the screen, please stop your
yes.
screen. Thank you.
Okay.
Yeah. Thank you very much. So
okay. Is it good? Huh?
Sharing my screen. Do you see my screen now?
Yes.
Excellent.
Cool. That's good. So today I would like to share with you our recent results on our efforts towards better understanding of optoelectronic processes in organic solar cells, specifically under short circuit conditions. And this work was done in collaboration between CPOS, Center for Polymers and Organic Solids at University of California, Santa Barbara, where I was working as a project leader, and also during my stay already at, as an assistant professor at Department of Physics of Nazarbayev University. So it is obvious for everyone that our intense environmental polluting and CO2 emission has a dramatic impact on our climate. And during only this year, which hasn't been finished yet, we already experienced globally quite many extreme weather conditions, which is a very strong sign that these issues with climate change should be addressed. And obviously, one of the best approach is to make a transformation from conventional fuels, which emit a lot of CO2, to renewable energy sources. And one of the key players among renewable energy sector is photovoltaics. So I strongly believe that it will play this leading role of renewable energy in the future also. And so far, most of solar cells are produced from inorganic semiconductors, similar like some classical approach is silicon. However, in this presentation, I will talk about organic semiconductors and organic solar cells. So you may ask me, okay, what is the reason for going from this established field of silicon photovoltaics and try to implement some new materials, which of course comes with many challenges. First of all, organic semiconductors provide additional functionalities which are not possible in terms of using conventional inorganic semiconductors. For instance, flexibility, transparency in the visible range, because it's tunable, or because of molecular structure of organic semiconductors. Wide range of possibilities to tune the band gap of organic semiconductors, because we have a possibility to change molecular structure of these organic semiconductors in a broad range. Low cost, because we use spin coating, so it's low temperature processing instead of high temperature synthesis, like growth of single crystals and doping of these materials. And also biocompatible, so it's environmentally friendly materials. So Organic semiconductors has already found quite broad application in field of organic light emitting diodes. So you can see this nice curved screens which are commercially available, and obviously it is big part of the display market nowadays. However, organic solar cells with this huge capabilities in terms of being integrated into existing or newly built buildings, and like semi-transparent coatings on different windows, and so far and so on. It is quite an emerging market nowadays, but with a great potential for future. So I would like to show here on this slide how performance of organic semiconductors evolve over quite short period of time. So if we compare silicon solar cells, let's say conventional inorganic solar cells, their performance, like of the best examples, are still higher. However, you see that organic semiconductors, organic solar cells, they do quite a good job in terms of increasing performance. Recent publication just a week ago, I haven't changed this slide, it's changing quite fast. In this year, it was reported already 19% efficiency. So it's coming closer and closer to this values which are provided by conventional inorganic semiconductors. And in the recent years, the main contribution to this increase in performance was achieved by substituting conventional fullerene-based acceptor materials by non-acceptor materials, and they, because of the difference in chemical structure, here we cannot change much. So here is fullerene, which is defined chemical structure, and some functionality which just allows solubility of this fullerene in different solvents. However, in this case, when we go from towards non-fullerene acceptors, we can change quite a lot, like side chains, like backbone, some heteroatoms. There are really many opportunities, I would say unlimited possibilities to tune this chemical structure and as a result, it will tune the electrical and band properties of these materials. So obviously, this gives much better tunability, and that's why in recent years we could see very steep increase in performance of organic solar cells. So let us focus a little bit on the structure and functional principles of organic solar cells. This should be highlighted in order for broader audience to understand better what it is and how it works. So usually it consists of an active layer. We call it bulk heterojunction layer because we have a mixture of two organic semiconductors. We call them donor and acceptor semiconductor. Band diagram is shown here. And we need a mixture of two organic semiconductors with different HOMO and LUMO energies. HOMO and LUMO stands for highest occupied molecular orbitals and lowest unoccupied molecular orbitals. If you have a comparison to inorganic semiconductors, it is a good correlation with the conduction and valence band of inorganic semiconductors. So the energy gap between this LUMO and HOMO could be considered as a band gap of a semiconductor. So we cannot use just one organic semiconductor, for instance, this blue or red, because of the excitonic nature of photoexcited events in this semiconductor. Organic semiconductor possess very low dielectric constant. That means that electrostatic interaction between electron and hole is quite strong. And there is some energy of like binding energy of exciton, which cannot be compensated with thermal energy at normal temperature, at like room temperature, common for operation of solar cells. Therefore, we need to create some quantum discontinuity at the interface between two materials, organic semiconductors. So we have LUMO-LUMO offset and HOMO-HOMO offset. This shift of energy alignment between two materials creates conditions when when this photo-generated exciton reaches the interface between donor and acceptor inside this bulk heterojunction layer. They can be split in free electron and hole and then contribute to electric current. So this is obviously the main component of organic solar cell. Usually it is considered as intrinsic semiconductor, so not dope, sandwiched between two electrodes, cathode and anode. So once we have already free charge carriers, which are separated at the interface between donor and acceptor material, free electron and hole can move along the networks of donor and acceptor materials towards respective electrodes. And this is driven by internal electric field because we have different work functions of this cathode and anode under equilibrium conditions. There is some uniform electric field and linear band bending inside the active layer. So that is the driving force for separation of these charge carriers. So they will contribute to photocurrent. So let us focus now on some main characteristics of solar cells, and that obviously is the GV curve under illumination. So if we measure current voltage characteristic of a solar cell under illumination, under short circuit condition, when the cathode and anode are shorted, we have some maximum current which can be measured in external circuit, which is called short circuit current, and that will be actually the main topic of our discussion during this presentation. But also there are other important parameters. This is VOC, it's open circuit voltage. It's voltage drop between cathode and anode under open circuit conditions. And also we have this fill factor, which shows how close the GV curve is to this ideal rectangular. So we would like to have something like this rectangular. However, in real life, this shape is not so I'm sorry about this. Not so nice, and that's why we need to take into account fill factor, which is technically is the ratio of this area which we get at maximum power point. So it's maximum power which we can extract from this, from the solar cell, and divided by the product of short circuit current and VOC. So this gives us fill factor, and we see that the performance, means most important parameter of solar cells, which is PCE, stands for photo conversion efficiency, is the ratio of the product fill factor VOC short circuit current divided by the input power, which is incident on the surface of this solar cell from the sunlight. So we see that all of these three main photoelectric parameters should be maximum, and they should contribute all to higher PCE. Another important parameter is wavelength, like spectral response of solar cell. Obviously, it depends on materials which we use. We will have different widths of this region of photosensitivity, let's call it like this. And this external quantum efficiency is technically the ratio of number of charge carriers, which photo-generated charge carriers which form photocurrent in external circuit under short circuit conditions. So defined by this numerator, we have short circuit current divided by elementary charge, gives us number of charge carriers, divided by the number of photons of monochromatic illumination at each wavelength, which are incident on the solar cell. So that is another very important and commonly measured parameter. So I would like to focus your attention on this point that all research labs in working in the field of photovoltaics, they always measure GV characteristics and EQE spectra. So this is the minimum what you need to do in field of photovoltaics. And that's why our approach is, in order to find a possibility to use this information, which is minimum required experimental data, in order to get as much quantity of information about recombination processes and charge extraction in solar cell as possible. So for this purpose, we need to consider three equally important processes of operation of solar cells. First, we need exciton photogeneration, and that will be happening in this active layer between electrodes, and distribution of this optical field will define where and how many charge carriers we will generate. For instance, here is shown for some device stack. Here is our active layer and interference picture for different wavelengths. So we definitely need to do it for all wavelengths of the solar spectrum and consider what part of these wavelengths will be absorbed, where these excitons will be generated. That will give us information on the generation of excitons within the thickness of the active layer. However, this is only first step, because in real life we have problems, and that comes with recombination. First of all, I mentioned about this splitting of excitons. So far we were talking about excitons, not of free charge carriers. In order to contribute to external current, this exciton should be splitted in free electron and holes at the interface between donor and acceptor material. That is possible only when excitons reach the interface before they annihilate. And moreover, they can also reach some charge, so-called charge transfer state, and recombine at the interface. So that is very short time scale process, up to 1 nanosecond, like maybe few nanoseconds, and that recombination is defined by Geminate recombination. Also, there is non-Geminate recombination. So once we already form this free electron and holes, they start to travel via respective networks in this bulk heterojunction toward electrodes. They can recombine. So it could be bimolecular, band-to-band recombination, bulk trap-assisted recombination, and also surface trap-assisted recombination. So we lose charge carriers while they are moving in the active layer. And another important parameter is extraction. So we care about building field, how strong field is inside the active layer to separate these charge carriers, and their mobility, because if we have high mobility of charge carriers, they can swiftly be extracted from the active layer and participate in the contribution towards the useful current, which we want. However, there is always a compromise between all these parameters, and we need to deal with that. So let us focus first on this simulation of charge carrier generation, which stands for actually exciton generation in the active layer. So we picked up different systems, so we have 3 non-foreign acceptor materials and 2 donor materials. So we had different combinations of these materials in different device structures. So we have so-called inverted device structure when anode is from the side where sun is approaching the solar cell, and so this is cathode. Zinc oxide works as a cathode, so cathode is from this side where sunlight approaches, or inverted structure, and conventional device structure when anode stands first on the path of sun when it hits the solar cell. So there are different combinations of materials and device architectures, and that allows us to have some generalization of our proposed technique, that it can work in different systems and different device configurations. That is important contribution. So here, for instance, we need to start with optical simulations. And for that, we need to know optical parameters like constants as a function of wavelengths for all layers which are involved in the device stack. So if you check here, we have quite many layers, including this active layer of bulk heterojunction mixture of two organic semiconductors. However, all others, they play a role of electrodes, and they also should be taken into account into this optical simulation. So we determined N refractive and K extinction coefficient spectra for these blends of different donor and acceptor materials by applying spectroscopic ellipsometry technique. I believe in this audience there are many people who know much better about ellipsometry, spectroscopic ellipsometry than me, so I will not focus much on this point. But we did all these measurements for all active layers and also for all electrode layers, which were involved in our study. So next step was utilization of available software for transfer matrix simulation. So it can give us optical field distribution and means generation rate of excitons within the active layer. So we can see here the X coordinate along the active layer and at different wavelengths. So we did it for different device architectures and systems of bulk heterojunction mixture. And once we have this generation rate distribution, we can proceed further, and there is necessary to calculate and determine the geometry combination losses before excitons are split into free charge carriers. And that is quite fast process. So it requires, in order to measure it directly as a function of bias, it requires quite complicated time-resolved techniques, which are available only in several labs globally. So our approach was to go in a most easiest approach, which can be scaled to many labs which are not so sophisticated. So the idea stands for the following. We have this, let's say, two-dimensional distribution of generation rate along the thickness of the active layer and along the wavelengths. So what we do, we need to integrate over wavelengths to get the spatial distribution of generation rate caused by all wavelengths within the region of spectral range of photosensitivity. Once we have this distribution, we can integrate it over the thickness of active layer, and times elementary charge, it will give us some theoretical short circuit current, means maximum possible short circuit current, which doesn't take into account any losses caused by geminate, non-geminate extraction issues. So it assumes that we extract everything, every single exciton which we generate in the active layer. Then what we can do in like real devices, we shine some monochromatic light with different wavelengths on our devices. And under this monochromatic illumination, we measure, so we measure first dark in the dark JV curve without illumination. Then we measure light JV curve, and the difference between light and dark gives us photocurrent. So this is this curve. At some reverse bias, which is about close to -3 volts, internal electric field is so strong that it separates very efficiently already splitted excitons, like free charge carriers, electrons and holes, and doesn't allow them to recombine non-geminately. So we kind of, by putting this a large reverse bias, we create conditions when we can neglect with the non-geometry combination. And that means that the measured saturated photocurrent at large reverse bias should be equal to the total amount of excitons generated in the active layer per second times some coefficient PG, which stands for the geometry combination prefactor. This geometry combination prefactor shows what percent of what part of photo-generated excitons actually made it to the interface and were split into free electrons and holes. So when we did these measurements, for instance, here we see generation rates calculated with this transfer matrix approach technique for different wavelengths. Then we calculate theoretical current, which had all monochromatic illumination. And here are experimentally measured saturated photocurrent. So the ratio between this saturated photocurrent to theoretical maximum current possible will give us this, geometry prefactor PG. So we did it for different wavelengths and got some standard deviation because it should be wavelength independent for different systems, for different mixture of donor and acceptors. We got these values. So we see that it's around, for instance, for PCE 10 COTIC flare, we get about 80% of all excitons actually split in free electron holes, which is not bad, but could be better. For instance, this high performance system has something like about, it's something around 0.95. So almost all photo-generated excitons can be split in free charge carriers. So once we have this geometry recombination prefactor, we can proceed further and define some parameter which is called mu tau. Mu stands for mobility, tau stands for effective recombination lifetime. So this single parameter, mu tau, quantifies non-geometry combination losses and charge extraction. Because we have mobility, so mobility obviously will define how fast we can extract charge carriers, and this effective recombination lifetime, which in case of multi-mechanism recombination dynamics in our solar cells, when we have presented both bimolecular recombination, trap-assisted recombination in the bulk, and trap-assisted recombination at the interface between active layer and electrodes, then this single parameter will give us some effective quantification of how much charge carriers we lose. Okay, thank you for some graffiti on my slide. We proceed further with the Hecht equation. Oh, unfortunately, we cannot get rid of this graffiti. It stays on the slides further. Guys, who made this nice art, please delete it because it kind of confuses the audience. I unfortunately cannot do anything with this. So we have our active layer in the device. And it really matters where exactly within this active layer these electron hole pairs are generated. Because it will define how for how long this charge carrier should be moving in order to reach respective electrode. And in case of intrinsic semiconductor, when we have uniform electric field in within the active layer, we can apply some well-known Hecht equation, which was proposed quite long ago. It was 1932, and with certain modification, quite widely and often used in optoelectronic devices. So it defines probability of extracting charge carriers as a function of their position, electron hole pairs position in the active layer, so position where they were generated. So we can see this this green line tells us what percent of photo-generated electron-hole pairs at each position in the active layer will be extracted from the active layer. And this takes into account, this equation takes into account mu tau, mobility and recombination lifetime. Then we have VBI divided by L, it's built-in electric field, how strong electric field inside, total thickness, obviously, of the active layer, and means that we can use these all parameters in order to calculate the probability of extracting photogenerated charge carriers. So once it is done, we can proceed to the second part of our what we actually added to this transfer matrix simulation script, when we can calculate the external quantum efficiency at each wavelength. So for this purpose, we already know this geometry combination prefactor. We know the extraction probability and generation rate. So this is given by analytically by Hecht equation. This is numerically calculated from transfer matrix. So we can integrate for each wavelength all over the active layer and get external quantum efficiency. So then we have experimentally measured quantum efficiency and calculated quantum efficiency as a result of synergy of numerical and analytical models, which are embedded in this equation. So then this mu tau would be considered as a single fitting parameter for fitting the experimental EQE. So let's say we don't know this mu tau product because it really depends on morphology, on materials which we use, on processing condition, and that is very important information in order to quantify extraction and recombination losses in these devices. So black curve here for each device system which we use stands for experimentally measured EQE. The red dashed line stands for the theoretical maximum EQE, which we would get if we don't have any losses for recombination and extraction. So once we take into account geometry combination, so we have this PG, its actual value. So we already reduced this external quantum efficiency, and this stands for the blue dashed line. Then we apply fitting of our theoretically calculated curve with the experimental one in order to get the best fitting and extract at which value of mu tau product we get the best fitting between experiment and simulation. So in this case, you can see we compare, so we determine this mu tau product for 3 systems. This is this gray bars. They define the value of this mu tau product. And also we perform way more complicated analysis, which implies application of voltage dependent, like bias dependent impedance spectroscopy in order to determine with independent method this mu tau product in the same devices. So you can see it's a very nice trend. So there is some obviously discrepancy in values, but it's not so much, and the trend is really good. So it means that by employing very standard techniques, measuring GV curves and EQEs, combining with readily available free access software for like Python script for transfer matrix simulation and fitting simulated and experimentally measured EQEs, we can get valuable information, quantitative information about extraction and recombination processes in organic solar cells under short circuit conditions. So another thing what is useful for application of this approach is once we know geometry recombination prefactor, we know mu tau product, and we can calculate probability of extracting these charge carriers within the active layer. We can do some predictions of of performance of our solar cells in terms of short circuit current. So for instance, here we see short circuit current as a plot, as a function of the thickness. So it's not position in the active layer, it's thickness of the active layer. So this is simulated curve based on transfer matrix, ideal one. And you see that it overperforms experimental data. So we did it for system PC 10COTSC4F. So the simulated curve, and these are measured curves. So we made 5 devices with different thicknesses of active layer, and we see that this measured short circuit current is smaller than theoretical one, which is obvious because we have some losses. So then if we take into account this calculated efficiency of extraction charge carriers with hash equation, and which includes this mu tau product, and also PG, geometry recombination prefactor, we get this simulated curve based on our approach, which fits perfectly to the experimental data. And what it tells us? It tells us that we can save a lot of time when we deal with a new blend system. Every time when some chemists synthesize new organic semiconductors, we need to find the best conditions for device fabrication in order to optimize it and extract the highest performance. The thing is that usually it takes you need to make dozens of devices, and it consumes a lot of valuable material and a lot of time. So in order to save this, we can just now, by employing this technique which we propose, we can make a single device with random thickness. For instance, it will be 70 nanometers thickness of the active layer. Then we can determine all parameters for like mu tau product, geometry recombination prefactor, and simulate this curve in order to understand at which thicknesses of the active layer will be the maximum short circuit current. And in this particular case, it will be somewhere at 90 nanometers. So instead of making a range of dozens of devices, and now it is possible to apply this in order to optimize the optimization process. It's kind of repeating words, but the sense I believe you got it. So we can make this optimization process very cheaper and more efficiently. And that matters a lot for experimental device physicists, because optimization process, before you start to learn something new about device physics, takes a lot of time and money. These materials are not cheap in terms of experimental scale. So additional information on this technique can be found in our recent paper in Advanced Energy Materials published earlier this year. And this is the link where you can get the code for transfer matrix and this fitting of measured and simulated EQEs. With this, I would like to thank you for your attention. This not very nice graffiti is still on my screen, but nevertheless, thank you for your attention, and you are welcome to ask me your questions.
Thank you, Viktor, Brus. It was a very nice presentation, and I hope you could get a new screen.
I hope it will not be engraved on my monitor.
No. Otherwise, the conference will probably pay for it. It's open for discussion if there are any questions.
Right.
I think, Alexander, do you have a question? I have a question, Viktor. I think there's a group at the Technical University of Denmark who works on organic solar cells, and I think they have a problem that the lifetime is very short, that they are kind of poisoned by oxygen. What's the lifetime of the solar cells you are working with? Are there any problems with it? Otherwise, it looks like a very nice gadget.
Mm-hmm. Yeah, sure. So first of lifetime, it is changing from system to system. And for instance, for this state of the art nowadays, one of the highest performing system and most studied PM6 donor and Y6 acceptor, it could be in the range of like 10 to -5, 10 to -6 seconds. So it's like a few microseconds. It could be also smaller. The thing is that it sounds quite short recombination lifetime. So if you compare this to silicon, but keep in mind that silicon solar cells, they operate with active layer of 300 microns in order to absorb all light and then convert it efficiently into electricity. However, organic solar cells operate in the range of active layers plus minus around 100 nanometers. So it's like 90, 110 nanometers, but rule of the thumb, it is something about 100 nanometers. So it's really extremely thin active layer. And even with such short recombination lifetimes, it is still enough time to extract charge carriers and reach quite high performance of about 18 or even recently published 19% efficiency, which is comparable to silicon.
Sorry, Viktor, I probably didn't express myself very clearly, but I thought about the lifetime of an entire solar cell. You know, we're talking about is it days or months, or I'm sorry about that, Viktor.
No, that's okay. That I think that is also an important question to highlight. In terms of stability, obviously there are some issues with stability. They are not so stable as silicon because it's organic layers. And again, it all matters also if you apply some filters for UV light, which is not so much in solar spectrum. So if we block this UV light, then it will not reduce a lot the photocurrent. However, it will significantly prolong the stability of these devices. Nowadays, there are available products on market which provide warranty for this T80 time. It's so-called T80 time is time during which the performance of solar cells drop from 100 to 80% of initial performance. That stands for something about 5 years. And definitely with good encapsulation, so it prevents contact with air and moisture, which is always present in air. We can reach quite decent stability. And again, with unlimited possibilities in synthesis different molecular semiconductors, it is possible to step by step go into the direction for synthesis more robust and stable organic semiconductors. So this work is going in parallel because it's emerging field and we still need to understand better physics of like photophysics, which is happening in the active layer of organic semiconductors in terms of optoelectronic processes. But of course, material science part is also in the process of improvement in terms of performance and stability.
Thank you, Viktor. Are there more questions?
Yes.
Sorry.
Yeah, you are welcome. Thank you for questions.
If there are no more questions, I'll close this session by thanking Professor Minamura, Professor Baranek, Professor Umatsu, Alexander Demchenko, and you, Viktor, for a very good presentation.